In this video, I'm going to cover the second half of the inference review packet that I handed out to you guys for review, and we're going to look at quantitative data. So we're going to start with means with one sample and doing a confidence interval. So the conditions you would need to check are random, 10%, independence, and nearly normal. For your nearly normal condition, if your sample size is less than 15, we're going to consider it small. 15 to 29, medium, and 30 or higher is large. Pretty much if it's medium or large, we're going to say that the central limit theorem applies. If it's small, I'm going to assume that it's from a normally distributed population and that the CLT will apply. This is going to be a one sample t interval. So the actual mechanics, I'm going to take my sample mean 310 plus or minus my critical t with 39 degrees of freedom. I can get this from my formula sheet or inverse t, 0.975, comma 39, and that critical value is going to be 2.022. I have my standard error, which is my standard deviation, divided by the square root of my sample size. So I'm going to go now to stat test, and I want to find t interval. I have the statistics, and my mean was 310, my sample mean, sample standard deviation 36, and my sample size was 40, confidence level 95%. So I'm going to calculate this, and I'm going to end up with 298.5 to 321.5. 298.5 to 321.5. And that's going to represent my confidence interval there. Okay, in the next question, I want to go ahead and do a test. How do I know? It's saying, is there strong evidence? Well, how do I know it's quantitative? I'm kind of going through that quickly. I see units here. So my conditions are random, 10%, independence, nearly normal, and independent groups. Okay, I don't have the data, so I'm going to have to rely on the sample size for the nearly normal. Independence, 10% randomization. Your name is going to be one sample t interval. So they're claiming that they want to get a goal of at least 26 miles per gallon. So that's going to be my parameter, mu equals 26. My sample statistic, or x bar, is 25.02. So when I'm calculating this, it's going to have n minus 1 degrees of freedom, or 49 degrees of freedom. So t sub 49 equals my statistic minus my mean over my standard error. So it's my standard deviation 4.83 divided by the square root of the sample size, which is the square root of 50. Okay, so let's take a look at doing that. We're going to go to stat test and t-test. I have the summary statistics again. My mean was my population parameter is 26. My sample mean was 25.02. My standard deviation from the sample was 4.83, and the sample size was 50. And I want to know, is there strong evidence they have failed to attain their fuel economy goal? They wanted at least 26, so failing would be less than 26. I'm going to calculate that. I get a test statistic of negative 1.43 and a p-value of 0.079. So negative 1.43. The probability t sub 49 is less than that is 0.079. So my p-value is higher than 0.05. I'd fail to reject the null. Okay, let's look at two sample tests and confidence intervals. So assuming we have two independent random samples, again, it's dealing with quantitative data. I have minutes. I have two groups. I have two samples, route A and route B. So the conditions I'm going to check are independent, random, 10% for each sample, nearly normal for each sample. If you actually had the raw data, you would need to make two histograms. And as we saw with proportions, I'm going to need to check independent groups. This is going to be a two sample t interval. That's what they're asking, 95% confidence interval. So route A, the average is 40, so I have the difference between my sample means. Route B, it's 43, plus or minus. I'm going to have some critical value with an unknown degrees of freedom, because that's going to come from my calculator, so I'm going to leave that blank right now. Times my standard error, which is on my formula sheet. It's going to be the square root squared divided by the corresponding sample size. He drove both routes 20 days each. So I'm going to end up with that. So in my calculator, I'm going to go to stat test, and I'm looking at a 2-sample t interval. So the mean of the first group was 40 with a standard deviation, I believe, was 2. Oh, no, what do I have here? 40 with a standard deviation of 3. And the sample size is 20. The second group, a mean of 43 with a standard deviation of 2, and also a sample size of 20. We're not pulling, we're only ever pulling for a 2 proportion Z test. Calculate. All right, you can see my degrees of freedom are 33, so I can get that critical T value now. So let me write this down. Negative 4.64, negative 1.36. So to get that critical T value, inverse T 0.975, comma 33 degrees of freedom, and that's going to give me 2.03. 2.03. Okay, let's look at a test next. Okay, your conditions are going to be the same. Independence, random, 10% for both groups, nearly normal for both groups, and independent groups, because we have 2 independent samples. This is now going to be a 2-sample t test. Okay. We're looking at reading scores of certified and uncertified teachers. So my claim is going to be certified minus uncertified, that there is no difference. I have some sample data. My sample mean from certified minus uncertified. So certified teachers, students had a score of 35.62 minus 32.48. So that's going to give me a difference of 3.14. So I'm going to have a test statistic. I'll come back and fill in the degrees of freedom. My sample statistic, 3.14, minus my population parameter, 0, over my standard error. So it's going to be the standard deviation of the certified group squared divided by the sample size, 44, plus the standard deviation squared from the second group divided by 44. And actually they told me it has 86 degrees of freedom, so I can fill that in now. Okay, so we're going to go to the calculator. We're going to do 2-sample t test. So for group 1, the mean was 35.62 with the standard deviation of 9.31 and a sample size of 44. Group 2, the mean was 32.48, standard deviation of 9.43, and a sample size of 44 as well. The alternative, they're asking, is there evidence of lower scores for under-certified teachers? So if these scores are lower, then this difference is going to be positive, so the alternative would be greater than 0. And we're not pooling, so calculate. Okay, test statistic 1.57, p-value 0.06, 1.57, p-value, probability t sub 86 is greater than 1.57, is 0.06. So at our 5% level of significance, we'd fail to reject. Okay, looking at a matched pairs test and confidence interval next. How do I know it's matched pairs? Well, I have kids doing push-ups. This actually is a mistake. This should be boys and boys. boys, this is like before and after they do exercise program. The context of this is a little off, otherwise it would be independent. You can't even see what I wrote. This is before and after, so boys and boys. Okay, so for match pairs, I'm checking independence, random, 10%, nearly normal. For the nearly normal, though, I'm just looking at the histogram of the differences all, and paired data assumption. Okay, no more independent groups because they're not independent. And this would be a paired t interval. Okay, so I would need to plug this data in my calculator, list 1, list 2, and then create a new list, L1 minus L2, to get the difference. And then what I want to do is just do a t interval on that list. So don't have the time to do that at this moment, but I'm assuming if I call this list 2, list 1, and I say list 3 is going to be L1 minus L2, and then I run my data on L3 and do a t interval based on that. So I'm going to take the mean difference, which is negative 7.33, plus or minus my critical value with 11 degrees of freedom, because I have 12 pairs minus 1. It looks like it's 1.8, times your standard error, your standard deviation of the sample, divided by the square root of the sample size, and that's going to give me a difference of negative 15.01 to 0.35. So that's a paired t interval. For the paired t test, okay, we have students taking an exam in June and then again in August. So your conditions are the same as above. You're going to have independent, you're going to have random, you're going to have 10%, you're going to have nearly normal, and again it's going to be the histogram of the differences, so one histogram, looking for it to be unimodal and roughly symmetric so that the CLT will apply, and you have your paired data assumption. Okay, so the name of this inference procedure is going to be a paired t test. So this assuming that June is list 1, August is list 2, and I create a new list. List 3 is L1 minus L2. Well, I have it set up differently. There's not one correct way to do it. You just need to communicate to your AP reader. My degrees of freedom here are 5. I have 6 pairs minus 1. So I'm assuming that my null is there is no difference. I have a mean difference, d bar, in this case of 5.3. So when I calculate my test statistic, t sub 5, it's going to be that sample statistic minus the population parameter over my standard error, 7.44, divided by the square root of 6. And just doing a t test on the calculator will give me this value, 1.75, and I end up with a p-value. This is not proper notation, but I'm a little short on time, of about 0.0699, so about 7%, which is high. I would fail to reject. Okay, let's look at the last pair of quantitative data, or the last inference for quantitative data. If we're talking about having two variables, and this is what we finished the year with, we're going to talk about a slope regression t-test and slope regression t-interval, and I'm just going to go through the conditions here. You have your straight enough, and this is where you want to talk about the scatter plot being straight enough. You have independence, and what you want to talk about here is the residual plot having random scatter. You have does the plot thicken, and essentially your residual plot, you want to see consistent spread, not a fan shape, and you have your nearly normal. And what you need to get there is your histogram of the residuals, or whatever display they gave you, needs to be unimodal and roughly symmetric, or the sample size needs to be large enough for your central limit theorem to apply. Okay, so taking a look at this question, I'll just kind of go through it in my textbook here, and we can follow along here. So you need to be able to read a computer output for the AP exam. We've talked about that numerous times. So I have an intercept and I have this variable. We're not doing anything with the intercept as far as doing a test or an interval goes. This is my coefficient, so this is going to be my b sub 1. So my beta sub 1 is 0. My b sub 1 is 11.8987. And going ahead and calculating a test statistic, t sub 16 equals my sample statistic minus my population parameter divided by, I have the standard error right here in the table next to the slope, 4.29. Calculating that gives me, it looks like 2.77. And then if I do TCDF, I need to multiply it by 2 because I'm assuming the alternative is there's no linear association, or the nulls, there's no linear association, beta sub 1 equals 0. The alternative is beta sub 1 does not equal 0. So I would do 2 times TCDF, 2.77, 999, and then 16 degrees of freedom to get this p-value of, it looks like 0.007. That's how I would cover a test. If we look at a confidence interval, it's going to be very similar. You're going to have your slope, your b sub 1, your estimate, plus or minus your critical value with 16 degrees of freedom, which I can get from doing inverse t. Say it's a 95% confidence interval. 0.975, you can't see what I'm doing. Inverse t, 0.975 comma 16. And that gives me 2.12. 2.12 plus or minus this 4.29. So I'm actually going to have to calculate this out by hand. 11.8987 minus 2.12 times 4.29, and the opposite. So it looks like I have a confidence interval of 2.80 to 20.99. That's how I do a slope regression t interval and slope regression t test. Hopefully you guys found this helpful. I'll see you after break.